Lightweighting reduces material cost, improves product performance, and shortens cycle times in injection molding. Small design decisions can produce large weight savings across a production run. In this video, we present 5 practical lightweighting techniques engineers can apply now with clear guidance and validation tips to use before committing to tooling. Trick 1. Optimize wall thickness. Consistent wall thickness is the most important rule for lightweight parts. Excessively thick areas add mass and often create sink marks, while overly thin walls reduce structural integrity. Select a nominal wall thickness appropriate for your chosen polymer and maintain that thickness across the geometry. Use smooth transitions between sections and replace solid, thick volumes with webs or thin ribs where stiffness is needed. Validate wall values with mold flow simulation or established engineering hand rules to ensure manufacturability and performance. Trick 2. Add strategic ribs and bosses. Ribs and bosses provide stiffness and mounting points using far less material than full-thickness walls. Place ribs where bending and torsion loads occur and align them to resist the expected forces. Keep rib thickness in the range of 40 to 60% of the nominal wall and include generous fillets at the root to avoid stress concentration. For screw bosses, use core outs and support ribs instead of solid posts to prevent sink and control shrinkage. Well-designed ribs often match the stiffness of bulk sections while significantly lowering mass. Trick 3. Employ hollow sections and core outs. Converting large solid volumes into thin-walled shells or internal core outs dramatically cuts weight. Housings, covers, and handles benefit from thin shells reinforced with internal ribs, which provide required stiffness with much less material. Tube-like geometries are preferable to solid beams for long spans. Hollow sections also cool faster, reducing cycle time and lowering cost per part. Always validate hollow or cored designs with finite element analysis and mold flow checks to confirm stiffness and impact resistance. Trick 4. Choose materials for strength to weight. Material selection dictates how aggressively you can thin sections while retaining performance. High modulus polymers and engineered blends allow thinner walls with maintained rigidity. Fiber-filled resins increase stiffness but also raise density, so evaluate stiffness per mass and not stiffness alone. In some cases, specialty polymers offer superior strength-to-weight ratios that enable more aggressive lightweighting. Compare supplier datasheets and run material trade-off studies to find the best choice for your design. Trick 5. Design for manufacturing and assembly. Lightweighting must be aligned with manufacturability and assembly to be successful. Minimize undercuts and complex side actions, plan balanced gate locations, and use sensible parting lines to prevent overpacking and weld lines. Consolidate parts where practical to eliminate overlapping material and fasteners, and favor snap fits instead of metal hardware when appropriate. Ensure correct draft angles and generous fillets for smooth ejection and shorter cycle times. Run DFM and mold flow analysis early to identify areas where material reduction could affect production stability or part performance. Effective lightweighting combines geometry, material science, and process-aware design. Apply uniform walls, strategic ribs, hollowing, optimized materials, and early DFM validation to reduce mass while preserving function and reliability. Tools like MaxNext provide instant manufacturability feedback and material comparison, helping you quantify weight, cycle time, and cost savings. Upload your next design to MaxNext and discover how much weight and expense you can remove without compromising quality.